Section 1.10 has examples of applications of some of the concepts we've used in Chapter 1. I'm going to work through one of the exercises as an illustration of how you can do the assignment for Friday. This is exercise number 9 on page 87. Take a moment and read that exercise, familiarize yourself with it. What we're wanting to do is predict the size of the urban and suburban populations in years successive to 2010. So one way to approach this problem is to make up some letters to stand for some of the things we want to study. Let's let X0 stand for the city population in 2010. Now we're actually given that, but you'll see in a minute why we'd want to do that. Let's call Y0 the suburban population in 2010. So, well, certainly what we know now is that the city population was 800,000. And the suburban population was 500,000. So I'm just going to put it in units of thousands here. Keep things a little simpler. You can do that or not. It doesn't really matter, but just make sure you identify things correctly. Well, the information given says that if we let x1 equal the city population in, say, 2011, and we let y1 be the suburban population in 2011, then a certain amount of migration has taken place. And one way to represent this is, or to calculate it, is just this way. We know that x1 will consist of, well, everybody who was in the city in 2010, 0, minus the 7% of the population, of the urban population that actually leaves. And then during that year, 5% of the suburban population moves in. So that adds to x1. So this is x, excuse me, that'll be y0. And this is actually 0.07. So that tells you the population in 2011. And it's not too hard to see. You can rearrange this just a little bit. Two terms of x0 give you 0.93, and the other term is 0.05. Same logic applies to y1. y1 will be the people that remained minus the 5% who left. And then what we do is add in the 7% of the urban population that moved into the suburbs. So there we have an accounting for all of the different groups, and if you reorganize this a little bit, you can write it as 0.07 x0 plus 0.95 y0. And notice I try to align the x's and the y's. The interesting thing about that is that you can rewrite that in terms of a matrix product. I think it's not too hard to believe that you can write vector x1, y1 equals some matrix times the matrix of values in 2010, x0, y0. What are the numbers that go in here? You can read them off. 0.93 and 0.07. The first column, and the second column is 0.05 and 0.95. So in any event, if you think of it in that fashion, you've got to do the arithmetic. You use the actual values that are given up above. Then you wind up with 769, first component, and 531. And those are in thousands. So 769,000 remain in the urban area and 531,000 remained in the rural area in 2011. And the reason we want to write it that way is that it's pretty easy to see at this stage that x2, y2, that is the population distribution in 2012, is going to be calculated in exactly the same way. We will have, starting out, x1, y1, the beginning of the year. By the end of the year, 93% of the urban dwellers will remain. 5% of the suburban folks will have migrated in. 7% of the urban dwellers will have gone to the suburban areas, and 95% of the suburban dwellers remain. So when we carry out this multiplication, this matrix multiplication, we get exactly what you would expect. 0.93 times 769 plus 0.05 times 531. That gives the number of urban dwellers remaining, and that comes out to be 741.7 roughly. And the same kind of calculation gives 0.07 times x1 plus 0.95 times y1, which is 558.3. So in 2012, this is the population. And you could actually continue this process indefinitely. For 2013, you would calculate the same thing, x3, y3. And that would give matrix times x2, y2. And the matrix here involved will be the same one as previously. The fractions are assumed not to change from year to year. That may or may not be an accurate assumption in the real world, but at least for the purpose of this illustration, we're going to make it. And let's see what happens. It comes out to be, I'm going to flip the screen over to where I've calculated this multiple times, 717,717.7 and 582.2. 15 and 582. So you notice that the urban values have gone down and the suburban ones have gone up, but by a little less. And what we can do is calculate this multiple times. What I've done here is use Mathematica to do the calculation for me. Here's the matrix we're using to multiply. Here's the initial vector of population. So if I evaluate the M cell and then the X cell, you get that. And just to illustrate how this works, to multiply a matrix by a vector, you do m dot x, and there's the result we expected. What I'm making here is a table of values for several years. Year number 1 is 2011, year 2 is 2012, and so forth. So by the time we get to 2013, 14, 15, 16, and so forth, to 2020, for example, you'll notice that the urban population is settling down toward about 613, 686. Those are the two values there. And in fact, we could carry this a lot farther. We can go some more steps beyond that. Let's go 10 more. With 10 more steps, you see that actually the urban population looks like has gone down below the suburban population. Let's go 10 more. Yes, the urban population is going to 547, and your suburban is now 752. 543 and 756. 542 and 757. I'm looking at the last value, 541 and 758. 541 and 758. 541 and 758. Not a lot changing at this point. So in other words, it appears that our little system is coming to an equilibrium, an important concept. This last value down here, 541.7 basically, and 758.3 seems to be about where the population settled down over these circumstances. So in the spirit of a sequence of numbers, you might even write this way. The population vector, x n, y n, when n gets bigger and bigger, as n goes to infinity side, seems to be getting closer and closer to something about 541.7 and 758.3. This is an example of a Markov chain. We have transition probabilities in a two-state system. It's pretty remarkable, maybe. You might not have expected that. You might have thought that the city would ultimately be depleted and everybody would live in the suburbs. That's not the case. We wind up with this equilibrium solution.